In this video, we are going to discuss, in a somewhat brief but still a detailed way, the most important distribution in all of probability and statistics. I mean, and that's not hyperbole. That is just fact. Any detailed study of probability distributions and then mathematical statistics has to include something called the normal or Gaussian distribution, right? It's the famous bell curve. And there's so many quantities out there, measurable quantities, that end up following this type of distribution. If not approximately, then exactly, right? And things ranging from your measurements of intelligence and aptitude. So your IQ um, scores, to scores on various tests like your SAT or GRE, your LSATs, your GMATs, all these things. Certain numeric economic measures and economic indicators or measurements or measurement errors in scientific experimentation. It goes on and on and on and on. The list is literally unending, right? So we're going to see what this distribution is all about. Talk about some of the parameters of this distribution, some of its properties, and then of course we want to be able to compute probabilities of random variables that follow this distribution, and then that's where we're going to see it's a huge, it's in fact it's on the opposite end of the spectrum as far as difficulty, whereas you have the uniform on one end, and then on the other end you have these Gaussian distributions. All right, so let's define what a normal slash Gaussian distribution is. So a continuous random variable, let's say x, is said to have a normal or Gaussian distribution with parameters and it's going to be interesting that we're using the parameters mu and sigma, right? And there's a reason why we're using the same symbols that we use to represent the mean and the standard deviation. In fact, those numbers are the parameters. They are what define they define a normal or Gaussian distribution. So we'll kind of know these in advance in general. There are some questions where we might be asked to find the mean and the variance. And it turns out that your mean can be any real number, right? So your mean can be any number from negative infinity to positive infinity, right? And then your standard deviation could be anything positive. So your sigma must be greater than 0. So again, so with these parameters, this is what the PDF looks like. So it's said to have a normal or Gaussian distribution if the PDF of x is this thing. So it's quite the monster. So I'm going to write this as 1 over the square root of 2 pi. So the 2 pi is under the square root, and then times sigma, that's the standard deviation. And then what comes next is an exponential, right? In fact, they sometimes refer to it as Gaussian. So it's an exponential function, but there's quite a bit of expression. The expression in the exponent itself is quite a bit much. So I'm going to use this notation to indicate that it's an exponential function. And then I'll say, so everything in the square brackets is actually in the exponent. In a second, I'm going to rewrite it in a way that you're more familiar, but I like to state it this way so you can clearly see what's in the exponent. And what we have is negative the quantity x minus mu squared, so we have that, and then all over 2 sigma squared, right? And that is the PDF. Now, what is the sample space? It turns out that the sample space is also the entire real line, right? And let me just fix one thing here. Make that my curly x, right? So that's the PDF of a normal distribution with parameters mu and sigma. Now, what do they look like? As soon as we have one of these new functions, we want to know their graphs. Well, this actually, the graph of Gaussians that look like this, it's the famous bell curve, right? They're called bell curves. So your Gaussian distribution tends to look like this, right? And it turns out where the distribution has its peak, you could say its absolute max, is exactly at the mean, right? So that the mean there is essentially where the distribution peaks. And in fact, it's perfectly symmetric with respect to the mean, right? So the vertical line x equals mu is a line of symmetry, right? So let's say like this. So f of x is symmetric with respect to the line x equals mu. And that means something right away. So if we know, for instance, now to actually prove the fact that the integral of this function from negative infinity to positive infinity is equal to 1, it's not a trivial exercise at all. You have to use some multivariable calculus and some change of variables and just a lot of fun stuff, actually. But it takes us beyond what we're focusing on in this particular video. However, it can be proven, right, that this function, if you integrate it, regardless of what the mean is and the standard deviation is, if you integrate it over the entire sample space, it will still equal 1, right? That it still has to be a valid PDF. So because it's symmetric with respect to mu, if the total area is 1, then it means that the mean would split it 50-50. So that means half of the distribution would be less than mu, and half of the distribution would be greater than mu. So basically, this area here, right, will be 0.5, and then this area here will be 0.5. And what does that mean about the mean? Well, it means the mean is also your median, or your 50th percentile. So the mean here is also your 50th percentile, right? So not only is it the peak, right, and there's a special name for where the distribution peaks. We call that value of x the mode. So essentially, the mode is the value that with the highest probability, right? So where does your PDF peak? Well, it turns out so the mode, the mean, and the median are all the same for these nice bell curves, right? Right. So you might be wondering, well, what role does the sigma play? Well, the sigma plays a role where it again, it still represents the measure of variability. So like how spread out is the distribution, right? So if you have a fixed mean, right, but then you vary the sigma, what you end up doing is you end up squishing the bell curve, you make it narrower in a sense. It still technically covers the entire real line, but more of the distribution is kind of centered around the mean, right? So the the smaller the standard deviation, right, the more your distribution is going to be like clustered around the mean. So let's just kind of graphically illustrate this. A lot of these properties, just because of the math that's involved, is so complex. We're just going to essentially do a lot of these properties graphically and so forth, right? So if, let's say, I have a bunch of normal distributions, but they all have the same mean. And so if I have something like this, where it is relatively flat, right? Or I have something like this, where it peaks a little bit higher, right? Or if I have something, this is going to be hard to do, but then it peaks basically like that, right? So they all have the same mean, right? But basically, so let me say, so this one would be sigma, let's say sigma 3, and then this one would have a sigma 2, not 3, so sigma 2, and then we will have this one that has a standard deviation, let's call it sigma 1. So the distribution that's you can say it in two ways. It's a flatter bell curve, or the values are more spread out. So you have more area down here, right, relative to the red and the blue ones. So the smallest of the three standard deviations would have to be the red one. So sigma 3 would then be less than sigma 2, and then less than sigma 1. So for instance, if the random variable that has this standard deviation would have less variability than the random variable that has this standard deviation, and similarly this one. So this one would have the most variability. So it's more spread out. So more spread out meaning a flatter, or it doesn't peak as high as the other ones, right? So that's essentially how you can sort of visualize what effect changing the standard deviation has on the shape of our bell curve, right? Now, changing the mean, you're just essentially rescaling your x-axis, right? So if you were to have two Gaussians, and with roughly the same standard deviation but different mean, then you might have something like this, right? And then here, so this would be your mu1, and then this would be your mu2, right? And then just thinking of this on the number line, then clearly mu1 would be less than mu2, right? So basically, just from from a purely geometric standpoint, we refer to mu as like the location parameter. So like, where is the peak, right? So this is your location parameter. And then the sigma, so your sigma would be like the scale parameter, right? Like how squished together are the values, or how spread out are the values. So in this case, your sigma is often referred to as the scale parameter. All right. Right now, so that's basically just graphically some of the properties of our Gaussian distribution. Now, what about the CDF? Well, the CDF is still an area function. So if you have a Gaussian that looks like this, and you have a value of x right here somewhere, and again, x could be any real number, right? The entire real line is our sample space, then the CDF would return this area, right? So again, we can write it down So, the CDF of the Gaussian would be the integral from negative infinity up to x. And then we would have to integrate that wonderful function, that 1 over the square root of 2 pi times sigma. And then if you wanted to write the e in the kind of the standard way, it would be e, and then you'd have negative the quantity x minus mu squared over 2 sigma squared, and then that would be with respect to t. So in fact, yeah, I need to change this to t, right? My placeholder variable there, and we would have to integrate this. But the interesting thing is integrating partially, not over the entire real line, but just a part of the real line. We know we don't have a nice closed form result for this. So no elementary antiderivative exists for this type of integral, right? So that's pretty sad, right? Now, if you think about it, well, okay, if we can't do it exactly, right? Think of how easy it was for us to do it for, let's say, a uniform distribution. If we can't do it exactly, then maybe we could do something and rely on tables. And yes, there are tables, and we will learn how to use those tables. But the fact is, because you have so many different Gaussians out there, each with a different mu and a different sigma, we can't possibly compile a table that would cover all those possibilities. Because think about it, the mean alone can be any real number. There's no way we can compile a table even just to cover the means. And then the standard deviation could be anything positive. Again, we can't compile a table that would cover all those possibilities. So what do? Well, it turns out there is a way that we can somehow like standardize, right? We can standardize or normalize any Gaussian to what we call a standard Gaussian or a standard normal, right? So if the mean is equal to 0 and our standard deviation is equal to 1, such a Gaussian, right? So such a such a normal or Gaussian distribution is said to be a standard normal distribution. Right? So if your mean happens to be 0 and your standard deviation happens to be 1, then it kind of simplifies things a little bit, right? But it's such a special thing, we refer to it as being standard, and we no longer use the generic variable x. We now reserve and use the variable z. So the standard normal random variable is denoted by, so we use uppercase Z, and then we'll still do our tilde, we'll put our n, and then it's now mean of 0, standard deviation of 1. It's still a bell curve. It still has all the properties that we talked about, but it's now centered at 0, and then our scale is 1. So it really does standardize things, right? So this is a little z as opposed to my big Z. So the PDF for this is a lot easier. So basically all I have to do is wherever there is a mu in my formula, just put a 0, and wherever there is a sigma, just put a 1. So it ends up being 1 over the square root of 2 pi, and then it would be times 1, right? And then I'll have my e to the negative, and then it's basically, so now I'm using z, so it's going to be z squared over 2 times sigma squared. But 2 times 1 squared is 2, so it's basically that. And again, z can be any real number, so that's the sample space, like this. So it's a lot easier, but it's still something that we can't integrate. Having this exponent of where your variable is squared, with the e as your base, it just makes the calculus really difficult, right? So we still can't compute this by hand, but there are tables that are now compiled, or yeah, they're standard normal CDF tables, right? So the CDF, which would now be my big F of z, which is the integral of this from negative infinity up to little z, integrating that function, so 1 over the square root of 2 pi, and then e to the negative, I'll switch to my t squared over 2 dt. So this CDF is found in many statistical tables and software packages. Right, so there is no getting around. Even if we wanted to do it by hand, we just can't do it by hand, and we're going to rely on our tables, right? But again, the tables are specifically for the standard normal distribution. So what does it mean if we don't have a standard normal distribution? Well, it turns out every normal distribution can be converted to a standard normal distribution by a process called normalizing or standardizing. So if x is a general, or just a regular, I don't want to say regular like it's demeaning, but if x is a normal distribution, random variable with parameters mu and sigma, then if I take my random variable x and if I subtract the mean and divide by the standard deviation, this actually becomes our standard normal distribution. And this process here is what we call either standardizing or normalizing. This now becomes z, and it follows the standard normal distribution, right? So this process here, let me just kind of highlight it. Right, so this is called standardizing or normalizing x. Right, so we can convert any normal into a standard normal. Now, just to kind of give you an idea of the key step in this process, and then what will happen is we'll end this video, and then in the next video we'll look at this table and then do more actual examples of the standardizing process. But basically this, if you have a normal random variable with parameters mu and sigma, and you want to find the probability that x is in some interval like this, right? We don't have tables for a whole bunch of different Gaussians, so what we have to do is convert this probability for x into a probability involving z. So what we do is we take this inequality and we subtract the mean from all 3 parts. So I'm going to do it in stages here. So first, I'm just going to use algebra on this inequality. So I'm going to take a minus mu x minus mu b minus mu, right? So algebraically that's the same, right? this is almost like where you're recentering it, like you're shifting the distribution. Remember what happens when you subtract, like if you have a function and you then take f of the quantity x minus 1, that you end up shifting it 1 unit to the right. Well, that's kind of what you're doing here. You're shifting it, you're recentering it. It ends up where you're recentering it is at 0, right? And then the next thing that we would do is then divide each part of this compound inequality by sigma. Now, because sigma is greater than 0, I don't have to worry about flipping the inequality signs. So then I'll take my a minus mu over sigma, and then I'll have my x minus mu over sigma, and then I'll have my b minus mu over sigma. But what happens now is this random variable is now my standard normal random variable. So we get to replace that middle expression with a new random variable, and we're going to call it z. So we have a minus mu over sigma, which is less than or equal to z, which is less than or equal to b minus mu over sigma. And then once we have this probability or this random variable standardized, we can then find the required values in whatever table or statistical software package that we're using, right? So this is the key step, right? So if we're starting out with a probability that involves a random variable that's not a standard normal, then we have to convert it into one that is standard normal. And then here I'll just say we will use our tables, right? And the use of the tables will be illustrated in the next video. So, grab some popcorn or maybe take a little intermission and then, tune into the next video. I'll see you then.